Hey, good morning, Bears. We have been working on gas laws, and so I want to kind of go through some of the calculations that you might have seen or have come across during this unit. We do want to wrap up this unit pretty soon, and so you will see a quiz tomorrow. So I just wanted to review some very basics, just go over some things with you that you might see on that quiz. All right. Now, we're talking about gas molecules, and so we started off talking about the kinetic molecular theory. The kinetic molecular theory, or what we call the KMT, is basically a description of gaseous behavior, like how gases behave. Remember, when we talked about matter, gases are really far apart from each other because they have a lot of kinetic energy that's kind of stored in them. And so they're constantly moving, unlike a solid that has very low kinetic energy and is, very tight. All the molecules are very, very tight, close together. So that's one of the key things you need to understand about gases. And the other key thing to remember from the kinetic molecular theory that is referenced in all of these formulas is that the kinetic energy of gases is directly proportional to temperature. I'm trying to be really careful how I write that. It's not that I don't know how else to say this. This is not equal to per se, like if kinetic energy has a specific number, then the temperature is going to have the same number. That's not what I'm saying. What I'm saying is that if kinetic energy is increasing, it's because temperature has increased. If the kinetic energy of a gas decreases, then the temperature has decreased. And so we call this a direct relationship. When you have a variable where one goes up, the other goes up as well. Opposite of that would be an inverse relationship or an indirect relationship where if one variable goes down, the other one goes up. Or if that variable goes up, the other one goes down. So opposite of what's happening. So I'm bringing that up because that's going to be coming up here shortly as we get into more detail about these gas formulas. Okay, I'm gonna, like I said, I'm trying to do a quick run through because I don't want to do a long recording. I want it to be short, sweet, and precise. The first law that we should talk about is Charles' law. Charles' law describes a relationship between volume and temperature. Temperature, when discussing gases, we need to talk about real quick, kind of on the side. Temperature in these problems need to be in a unit called Kelvin. Kelvin is just another unit for temperature. Its unit is capital K. You might see some problems where they give you Celsius. So in order to convert Celsius to Kelvin, you take Celsius plus 273, and that equals Kelvin. So in all of these problems, anytime you have temperature, make sure your temperature is in Kelvin. All right, so getting back to Charles' law, describes a relationship between volume and temperature. The formula is V1 over T1 is equal to V2 over T2. What does that mean? What we're doing in these problems is we're kind of looking at gases in an initial state. So let's say I have a balloon, and that balloon is at a given situation, a given system. Let's say I blow up the balloon in my living room, right? It has a certain constant temperature and it has a certain volume, and it's just kind of at a static state where I blow up the balloon, I tied it, there it is, it's existing. Now the V2 T2 would be what happened to that balloon if I start messing with the volume or the temperature. We're not looking at anything else. We're not looking at other possible variables like moles. We're not looking at pressure. We're simply looking at volume and temperature. So here's a really good example of trying to understand Charles' law. Well, I'll get to that in just a second. Let's finish talking about this. This volume and temperature has a direct relationship. Anytime you see that something is being divided by something, it usually is indicating a direct relationship. A direct relationship, remember, is when one goes up, the other goes up. So if from V1 to V2 my volume increases, then my T2 would also increase if I'm seeing an increase. And so that's just kind of a way that we look to see if that's one way when working problems. I would tell my students, this is how to check your work to see if you're on the right track. Because if your answer ends up with a V2 higher than the V1, and then your T2 is lower than T1, there's some sort of calculation issue. That's not scientifically. If this one goes up, then this one will go up as well. Okay, so we call this again a direct relationship. And then to graph a direct relationship, very generally, it would look something like this. So we have volume here on the y-axis, temperature on the x-axis, and we see this line that kind of cuts through in the middle. It's a direct relationship. Okay. All right, so to go a little bit further into what Charles' law, and you've seen all of these happen in action. A really good one that probably a lot of people can relate to is a balloon in a hot car. Right, so you go to a birthday party, you have a balloon, and it's in the car. Well, that balloon was created, I guess you could say, was blown up, not in a hot car, right? It was probably blown up in some more comfortable atmosphere where somebody was decorating for a party. But now the balloon, so this is before a car. Now the balloon is in the car. What happens to balloons when they're in the car is the temperature is going to increase, especially in the summer, right? The temperature is going to increase. And so what's really happening is because the temperature is increasing, it kind of refers back to, remember, the kinetic energy is being related to temperature. If temperature is increasing, kinetic energy is increasing. So those gas molecules are already moving really fast because they have a high kinetic energy. But now they're like really moving around, and they start pushing on the wall of the balloon because they're trying to increase their volume. So temperature is increasing. Now they're going to start trying to increase their volume to make room for that extra kinetic energy that's taking place. And what happens to the balloon? It pops. Vice versa, if you take the same balloon over here, and you put it, and you might not have ever tried this one, but I challenge you to try it. If you take a balloon, you blow air into it, you put it in a freezer, now we're decreasing temperature, we should see a decrease in volume. And so what you would find is that the balloon should have shrunk or should have gotten smaller instead of larger. So in a nutshell, that is Charles' law. Charles describes a relationship between volume and temperature. It's a direct relationship, and the formula is V1 over T1 is equal to V2 over T2, and this is the general graph for that relationship. All right. Okay, the next law that we need to talk about is Boyle's law. Boyle's law. Boyle's law investigates a relationship between pressure and volume. The formula for Boyle's law is P1 times V1 is equal to P2 times V2. Notice how in Charles' law we were dividing volume and temperature, but here in Boyle's law we're multiplying pressure and volume. And this type of mathematical equation, when we're comparing variables, is what we call an inverse or indirect relationship. You might hear it called both. That graph with pressure over volume looks something like this. And like I said, this is an inverse relationship. That means if, for example, let's say pressure is going to increase from P1 to P2. So let's say I had a 3 here, and now my P is a 5. I'm just using numbers. So my pressure increased. Well, let's say my volume was a 2. Then I would expect my volume to now be a 1. The inverse, so if pressure is increasing, then volume would decrease. Vice versa. If pressure decreases, I should see that volume would increase. So it's a opposite of Charles' law, where if volume was increasing, temperature was increasing. In here, if pressure is increasing, volume is going to decrease. Let's talk about pressure real quick again. Pressure, it comes from the gas molecules hitting the walls of the container, whatever the container is. Remember, gases, according to kinetic molecular theory, technically don't have any volume because they're occupying a container and they're moving around. I could have, let's say, 5 grams of helium. And those 5 grams of helium are floating all around in a constant motion. Now, remember, the gas is going to keep going in a constant straight line motion, again, according to kinetic molecular theory. But as soon as it hits the wall of the container, it's basically going to bounce off and go in another direction, and then it's going to hit the wall of the container again, and then it's going to bounce off and it's going to go in another direction, and then it's going to hit the wall of the container again. It's going to keep doing that. And so when we talk about the volume of a gas, we're basically just looking at the volume of that container. So if the volume of this container was 10 milliliters, let's say it's like a little beaker. That's a really small beaker. Let's say 100 milliliter beaker. Then we would say that the volume of that gas is 100 milliliters. Now, the larger the volume, the larger my container. Let's say I took this same amount and I put it in a 50 milliliter container. Okay, so my volume has now decreased. So my V1, this is my V1 now. Here's my V2. This is going to greatly affect my pressure. Why? Because I have, let's say I still have 1, 2, 3, 4, 5, 6. So I'm still going to use these 7 little dots, even though this is just to give you an idea. So notice I still have the same amount of mass of helium. I haven't changed my quantity. I added one too many. But you still kind of get the idea. Notice how in my first picture, the helium molecules are far, have some space to move. But now I've changed my container, and now there's not as much room to move, which means every time those gaseous molecules are moving in a constant fixed state, it's moving in one direction, hits the wall, it changes direction, hits the wall, moves in another direction, hits the wall. It's hitting the wall of the container much more frequently than it would in the larger container. And so because of that, pressure increases. So this is just a visual to try to help you understand, okay, well, if my volume is decreasing, why is pressure increasing? It's because you still have the same amount of gas molecules, but now it's in a much smaller container and still moving at a constant rate, right? Because we haven't changed the temperature. That's going to increase the pressure, and vice versa. If I had gone from the 50 milliliter beaker to the 100 milliliter beaker, my volume increased, so therefore my pressure would decrease, because now the molecules have much more space to move and they're not hitting the walls of the container as frequently as if they were in the smaller beaker. Next law to discuss is Avogadro's law. You've heard that name before. Oh gosh, I'm terrible with writing it. Avogadro. Sorry. Avogadro's law. We've talked about Avogadro. Remember Avogadro's number? Avogadro's law looks at volume and moles. Volume and moles. Notice all the law, Charles' law, Boyle's law, Avogadro's law, all are looking and analyzing volume. And then the second variable it just depends on what that law was. But all of them so far have to do with volume. The formula for Avogadro's law is V1 over N1 is equal to V2 over N2. The graph for Avogadro's law, where volume is on the y-axis, moles is on the x-axis, looks very similar to this, just like we saw in Charles' law, which would indicate to us that this is a direct relationship. Direct relationship. If one goes up, the other goes up. If one goes down, the other goes down. So that's what's kind of happening here. All right, now let's talk about Avogadro's law and put it into terms and the things that you've seen. And it's easy to use the balloon analogy because we've all dealt with balloons and we have a good idea from personal experience what happens to them, as we're inflating them or deflating them or whatever. Now, if I have a balloon and it's not blown up all the way. Maybe it's like one of those super massive balloons, and I've just thrown a couple of puffs of air into it. It can still be inflated, right? So if I add more air to the balloon, that would be me increasing the moles of the balloon. Therefore, the volume of the balloon would increase and it gets bigger. So just imagine someone blowing up a balloon. If you're adding air to it, which means I'm adding moles, which would be my N, there's more of them in the container, so they're going to try to occupy more space, and therefore the volume of that container, in this case the balloon, is going to increase. Vice versa, if I have this balloon here and I let some of those moles out by releasing air, well, then the volume of my balloon is going to get smaller. And so it's a very simple idea of, if I'm adding more air to the balloon, the volume of the balloon is going to increase. If I'm decreasing the air in the balloon, then the volume of the balloon is going to decrease. Another law that you should have seen in the notes is Dalton's law. Dalton's law does not compare multiple variables. It's just looking at what we call partial pressures. Partial pressures. Pressure, again, is the gas molecules, the number of times and the frequency with which they're hitting the walls of the container. We have different units for pressure. I'm just going to kind of bring that up right now. Pressure can be measured in ATM, which is atmospheric pressure. Pressure can also be measured in kilopascal, or kPa. We can measure pressure in torr. We can also measure pressure in millimeters of mercury. Why does pressure have all these different units? Well, it depends on what the scientist is using to measure the pressure. And so we're gonna stick, for our purposes, we're gonna stick to ATM, but you do need to understand that there are different units for pressure, and it has to do with there being different tools to measure pressure. For example, a barometer, an anemometer. I think that there's a I can't think. My brain's drawing a blank, of course. But there are different tools to measure pressure, and that's where all that is coming from. All right. And all Dalton is saying is, okay, if I have one container with a gas and it has a certain pressure, let's say it has X ATM pressure, and then I have another container, it has Y pressure. And then I have another container that has Z pressure. If I take all these pressures and I add them together, then I would get a grand total pressure. So it would be, you would just do X plus Y plus Z. And then that would give you the total pressure. Now, it sounds easy, but these problems are way more complicated than you might imagine. Why? Because you have to account for the volume of the container, and you have to consider how many are in there. And then, what's your final container going to be? There are a lot of factors here. But for our purposes, if you can understand that Dalton's law is all the partial pressures added together, then we're on the right track. There's no graph that goes with Dalton's law because we're not comparing pressure and temperature or anything. We're not comparing multiple variables. We're only looking at pressure. All right, final slide here. To put all these laws that were observed by various scientists and try to really understand the behavior of gases, the scientists put together something they called the ideal gas law. Now, ideal gases helps us in a laboratory setting understand or predict gaseous behavior. But we don't have ideal gases, we have real gases. And so again, we just use this as a way to predict behavior. But with that in mind, gas molecules don't necessarily work in the most ideal situation ever. For example, kinetic molecular theory says that gaseous collisions, when two gas molecules come together and they tend to be on the same trajectory, where they're going in one direction and the other is going in the opposite direction, they're about to collide with each other, right? Now, kinetic molecular theory says that basically they just bounce off each other with no exchange of energy at all. Now, if that was the case, gas molecules would never work in a chemical reaction. Secondly, we observe that when objects do collide, there's an exchange of energy, right? Just imagine like when a car crashes into another car. Depending on how fast that car was going or whatever, will determine what kind of exchange of the collision, and then it will affect what direction it ends up going back in. And yeah, we don't need to go into all of that. Those of you who are taking physics, you'll understand more of that next year. But to get back on track, we still use ideal gas laws as a method of prediction. And so when scientists were combining all of Charles, Boyle's, Avogadro's, Dalton's all together, they came up with this grand formula, and it's PV equals nRT, where P equals pressure, V equals volume, N equals moles. And I want to point something out here. It goes along with Avogadro's law too. You cannot use grams here. It has to be in moles. How do we convert grams to moles? We take the mass that it gives us and we divide by the molar mass of that chemical. Remember when we did that before? Okay. So your N is moles. It needs to be in moles, not grams. Then we have R, which I will get back to in just a second. R is a gas constant, and depending on your unit of pressure, it will, if your pressure is in ATM, this is like ATM per liter, per mole, per something, this is always going to be a constant number. So this is not a number you have to memorize. It's going to be given to you. All right. PV nRT, temperature. T is temperature. And remember, your temperature needs to be in Kelvin. If it gives you Celsius, then you do Celsius plus 273 equals Kelvin. And this ideal gas law, again, combines Charles, Boyle's, Avogadro's all in one. And it helps us analyze the system of a gas. The system of a gas. So if I have a gas and an ideal, I guess, situation, I could know certain variables of this system here and be able to calculate what I don't know. So for example, if I know the pressure and I know the volume and I know the temperature, but I don't know how much gas is in this container, then I can solve for N. How would we solve for N if I'm using PV equals nRT? I'm not going to give you real numbers right now, but if we were solving for N, how would you rearrange your formula to solve for N? Well, if I want to get N by itself, I need to get rid of R and T. So if I'm multiplying R and T times N, to get rid of it, I need to divide by R and T. So now these guys get canceled out, and we're left with N equals PV divided by RT. And you just plug in and solve for N. Being able to manipulate your formulas is key here. And so I just kind of want to go through a couple of these again real quick. I don't want to take too much more of your time. If we're looking at Charles' law, V1 over T1 equals V2 over T2, and let's say I need to solve for T. Now, I know you've heard this terminology before. When you're solving for this unknown, and you have a fraction that, ultimately a fraction, that is equal to another fraction, the way you need to solve is, somebody referred to it earlier as the butterfly method. Or you cross multiply in more technical terms. So here in this situation, to solve for T, I would start first by doing, I would have T1 times V2 is equal to T2 times V1. We're trying to solve for T1. So if I want to do T1 by itself, I need to get rid of V2. If I'm multiplying the two, then I need to do opposite of that, which means I would need to divide by T2, both sides. These cancel out. And so then we're left with our formula being T1 equals T2 times V1 divided by V2. In this situation of Boyle's law, where we have P1 times V1 equals P2 times V2, and it says, okay, you need to solve for P2. Well, this is already, half the work is already done for you. If I'm multiplying P2 times V2, and I need to do opposite of that, so I need to divide the V2. So V2, divide both sides by V2. These cancel out. We're left with P2 equals P1 V1 divided by V2. This is basic Algebra 1 manipulating formulas. So if you have any questions or you get stuck, just let me know. I would, if I were you, go back, take notes over each slide, and you'll be seeing a quiz tomorrow. Email me if you got any questions. See you guys later.